Hello again, Calc AB students. Mr. Ray, I'm back with a little video for you about our work for Thursday and Friday this week. So if you're in Ms. Hoagie's class, thanks for tuning in, and hopefully you guys get this on Thursday. I wanted to make a small correction to the calendar for everybody, not just Ms. Hoagie's class. But I noticed on the calendar that one of the problems that got assigned is actually one that you wouldn't know how to do just yet. The page is 537, and one of the problems that stuck in there on me was problem number 21. I think maybe Ms. Hoagie uses the same assignments. And if you have 21, that one involves arcsine, and we have not done inverse sine yet. So you can probably just skip over 21. If you're in Ms. Hoagie's class, maybe check with her to see if there's a different one she wants you to do instead. If you're in my class, we're just going to skip over that one. We'll come back and talk about arcsine in chapter 5, and we'll be able to do a little bit more work with that. So with that said, what I'd like to do is introduce you to another application of derivatives. So we've done curve sketching, which is really powerful using a use of derivatives. We've done a little bit of optimization earlier this week, and that's a nice application of derivatives as well. For my class, hopefully you found the video of me working through all the homework problems. I broke it down for each problem, so hopefully if you were stuck on one, you were able to work through that. And the next application we're going to do is something called L'Hopital's rule. So that's right, you heard me. If you happen to be in French class, you know what I'm talking about. L'Hopital's rule. Yeah, he was a French mathematician, and oh, I see that my keyboard here and the old Zoom let me down. There should be a circumflex over the O there, because in French, there's a lot of words where there used to be an S after that vowel, after that O, but then we don't say it. So L'Hopital's rule, it literally means the hospital's rule. And that was because that was the mathematician's name. So his last name was L'Hopital. You'll see it actually, the hospital's rule, in other textbooks. Dr. Larson uses the formal French name for what's his name here? Guillaume L'Hopital. So he was alive from 1661 to 1704, and so coming along a little bit after Newton, and figuring out something interesting about the relationship between a function, and when you want to find the limit of a function, and what derivatives can actually help you do with that function. And so we're going to take a look at L'Hopital's rule here, and then we will do a couple of application or examples of it really quickly, and then I'm going to just end it right there, and then Ms. Hoagie can fill you in on more on your class, and I'll fill you in more of my class on Friday. So here we go. L'Hopital's rule says this, well, let's have two functions. Oops. Let f and g be functions that are differentiable on an open interval a to b containing c except possibly at c. Okay, so it's differential everywhere except maybe at c. Okay, and then we have another assumption here. Assume g prime of x is not equal to 0 for all x in the interval a to b. Okay. Then, okay, if the limit as x approaches c of f of x over g of x produces an indeterminate form oh goodness Oh no. Indeterminate form. Zero over zero, or infinity over infinity. Then the limit as x approaches c of f of x over g of x is equal, and this is the cool part, to the limit as x approaches c of f prime of x over g prime of x. What this does is it gives us another kind of tool in our toolbox when we run into a problem where we're taking a limit and all of a sudden we get one of these 0 over 0 or infinity over infinity ones. Okay, and because when that happens, sometimes you would have to resort to some other techniques. Might be multiplying by one, you know, like multiplying by 1 over x over 1 over x. Might be invoking a squeeze theorem. Sounds familiar. Yeah, there's lots of possibilities where, you know, other ways we could go with it. But L'Hopital's rule actually simplifies so many of the different derivatives. Sorry, I just did a video on integrals for Calc BC. You don't know what that is yet, but you will soon. And so let's take a look at some old favorites that we maybe have and see how L'Hopital's rule can be used to help us out. So I'm going to start off with the limit as x approaches 0 of sine of x over x. And you probably are all like, oh man, that's right. That's one of those squeeze theorem ones. And you're right, it is. Okay, because what happens in this case? If you put 0 in, you get sine of 0, which is 0, over 0. Okay, which means it is an indeterminate form of 0 over 0. Okay, and that means we can invoke L'Hopital's rule. Now, if you want to abbreviate it by LH and put a little arrow pointing at your equal sign, perfect. That's a great way to show your work and to indicate to your grader, whoever that may be, okay, that you know how L'Hopital's rule works. Now, what is the derivative of sine of x? It's cosine of x. What's the derivative of x? 1. Now, what happens if we put in 0? We get cosine of 0 over 1. And sure enough, the cosine of 0 is 1. So there's a great example of how L'Hopital's rule works. Rather than mess around with that squeeze theorem, we can just apply L'Hopital's rule and get through our problem quite nicely. Sound good? Right? Pretty cool, right? Yeah, it's super fancy. And it's super easy. And it's a lot quicker than the old way we were doing it, right? Think about when we were doing curve sketching, right? Like if we had this problem, limit as x approaches -1, x squared minus x minus 2 over x squared plus 1. Oh, sorry, minus 1. My bad. Yeah. Okay. Well, if you plug in 1, let's see. We get 1 for x squared minus -1, which is then 2, minus 2. Oh, that's 0. X squared minus 1. Oh, that's also 0. So this is 0 over 0 case. So let's apply L'Hopital's rule and see what happens as x approaches -1. x approaches -1. Well, what's the derivative of our numerator? Well, let's see. It's 2x minus 1. And what's the derivative of our denominator? Ah, 2x. Well, now look, you could just direct substitute -1 in there, right? Yeah, you get 2 times -1, okay, minus 1. And we get negative over negative, so we get 3/2. Well, that shouldn't work out. All right, so we get a positive 3/2. Now, the other way we would have done it in the past, right? We would have factored the numerator, factored the denominator, canceled out the removable discontinuity, and done all that. But if all we were interested in doing was just figuring out what the limit as x approaches -1 is, L'Hopital's rule provides us with a really easy way to do that. And that's really it, guys. That's all that's involved in L'Hopital's rule. Make sure that it's an indeterminate form. That is the first thing. If it's not indeterminate, this doesn't work. Okay, if you don't get 0 over 0, infinity over infinity, or you can have negative infinity over negative infinity or whatever. It's got to be those indeterminate forms. In fact, they're all listed in the theorem, which is on page 531. So I would direct you there to check this out. Oops, I need a pen, not an eraser. There we go. Page 531. There's a nice listing there at the end of theorem 7.4. Shows you all the indeterminate forms that this will work for. Now, this is coming to you from chapter 7, which is way, way ahead of us in the book. Okay, so don't look at the examples in there too closely because there's a few in there that you're not going to understand. Okay, we haven't talked about exponential functions yet. Okay, we haven't talked about natural log functions yet. We haven't talked about arcsine yet, which is what kind of cracked me up that one snuck into my my listing of the problems. But we have done a lot of work with derivatives though. And so all the problems that I went through and selected for my kids, and I think the same is true for Ms. Hoagie, are ones that you should know how to do the derivatives with. My apologies if number 21 ended up on your list too. Well, that was my bad. I didn't catch that one that had an arcsine in it. So with that, good luck with L'Hopital's rule, guys. It's a fantastic way to evaluate a limit. And it just does so in a much easier fashion than maybe some of the ones we've seen in the past. So, all right. Thanks so much, guys. See you in class.